This example doesn't really follow any of the rules I've shown so far. That's why it's a great one to do. If I just start with my normal idea of plugging in infinity, this is going to go to infinity, and then e to the negative infinity, you might need to think about the graph for that. You should know that e to the x looks like this. So as x approaches negative infinity, this graph basically goes to 0. So this becomes infinity times 0. Well, that's not exact. We don't know what the answer is here either. This is also another indeterminate form. True, it's not 0 over 0, and it's not infinity over infinity. But infinity times 0 is another thing where, like, well, infinity seems like it should be getting really, really, really big, but 0 usually makes everything 0. So what's going on here? But like I said, L'Hopital's rule talks specifically about things either being 0 divided by 0 or infinity divided by infinity. So to approach this with L'Hopital's rule, I am going to first have to rewrite this expression in a way that makes sense and makes it one of the indeterminate forms that we actually know how to handle. That expression, x e to the negative x, can be rewritten without negative exponents to look like x over e to the x. So this is going to be equivalent to the limit as x approaches infinity of x over e to the x. Excuse me. Yeah, that's good. So what happens? If x goes to infinity, this goes to infinity. What happens with e to the infinity? That's also infinity. So I do have L'Hopital's form of infinity over infinity as an indeterminate form, and I can apply the rule. The rule says take the derivative of each part separately and take the limit again. So I'll look at the limit as x goes to infinity of this derivative, which is 1, divided by this derivative, which of course is itself. And as x gets huge, this gets huge, so we get the 1 over infinity, which is not an indeterminate form. This is going to equal 0. So the limit as x goes to infinity of x e to the negative x equals 0. Yep, 0.